All right, our next speaker is Sebastian Murgueitio Ramirez from the University of Purdue, who's going to talk about dynamical dispositions and geometrical structures.
Thanks for this. Yeah, so the talk today, what I want to do is to show you that there is an interesting parallel between two debates going on in the metaphysics of science or metaphysics of physics. And I want to draw some connection, or I want to draw some attention to some interesting connections between these two debates that, as far as I've noticed, nobody has explicitly shown. Oh no, it's okay. So here is one of the two debates. If you open like a physics textbook, or you open, I don't know, a physics article that is on general relativity or quantum field theory or even classical mechanics, you will see reference to symmetries all over the place. You go to Wikipedia too, and you open many articles in Wikipedia about physics, you see the term or the notion of a symmetry there. And so the point is, symmetries seem to be everywhere in physics discourse, in both, in all fields, really, or 99% these days. And so if you're a philosopher of physics trying to understand, for example, what theories are telling us about the world, you might wonder, what is this thing, symmetries, that seem to be used in these theories? What is this telling us about the world? Or can be even, how could we be, if we want to be realist about at least some of this, about some parts of these theories, we seem to have to think about what symmetries are, or what are they saying, or what do they say about the world. So here is one option that has been developed in the last 2 decades, more or less, that I think has a longer history, which is symmetries are, in a sense, physical structures or properties of physical structures in the world. You will recognize something like this in ontic structural realism, and in particular in Stephen French's project. But many other structural realists have thought that, in a way to understand this symmetry talk is to think, to reify it in some way, either as properties of concrete structures in the world, or as structures themselves, like the symmetries as structure out there. Depends on the details, but that's kind of the rough idea. Kerry Mackenzie has also developed some versions of this, but she has changed a little bit her position, and she has a more qualified structural realism, as far as I can tell from some of the more recent papers. So this is the structuralist approach to making sense of symmetries. On the other hand, here is another approach. Symmetries aren't physical entities at all, or properties of physical entities, but useful mathematical tools. They are just very useful to do math. They are useful ways of codifying. If you have a very long equation with a lot of things, well, maybe you can write that as a simple group, and then you just don't have to deal with this very long list of things. So to put that. Who says this? Well, for example, Arvind Chakravarti, in an exchange he had with Stephen French, kind of supports something like this, in part because, as we will see, it's very hard to make sense of symmetries from the point of view of a dispositional realist, which he is a dispositional realist. So there is this debate about symmetries in the literature of scientific realism, between structuralism and dispositionalism. Now here is another debate in spacetime. So the previous one was not about spacetime, but consider the following one. In the context of spatial relativity, well, the standard story that you learn in textbooks and things like that is like that if you are in a certain frame and you move with certain velocity with respect to another frame, objects contract or time dilates and things like that. So this person said the teddy bear is 1 meter, but that person said the teddy bear is 0.8 meters. It's a very big teddy bear, 0.8 meters, and then they disagree about that. And like, how do you make sense of that? Well, the standard, but with a star because history is complicated. But the standard account in physics is that you appeal to the geometry of spacetime and you say, look, changes in length or changes in time intervals and all of these kinds of things really are just a result of the fact that we inhabit a world with a certain geometry. What geometry in this case becomes geometry, and so things do what they do because or in virtue of inhabiting this kind of geometry, and that's it. That's kind of the explanation. They do these drawings with vectors and things like that, but that's kind of the essential laws. Who defends this, either explicitly or implicitly? Well, first Minkowski, very explicitly in his 1908 paper. Einstein at some point says things like this, and from the philosophy point of view, Michael Friedman and Tim Nodling have said things like this. But here is another attempt to understand, for example, length contraction, which can go roughly like this. Or originally at least, you say, well, actually, Lorentz, for example, you say things do contract because the forces change under boost, and you can show from electromagnetism that, for example, an electron around an atom, the shape of that, just from Maxwell's equations, is such that it looks contracted or it looks distorted in certain ways. No space-time, look at Lorentz, look at the Maxwell equations and the transformations of that, and you can recover these things. There are many variations of that, and this view didn't become very popular, but you can find instances of this in, for example, John Bell, Einstein at some points, and Harvey Brown most famously. But he doesn't want to talk about intermolecular forces necessarily, but he talks about the dynamics of whatever are the laws that govern the matter. Whatever those laws are, the dynamical laws, look at them, look at their properties, and then space-time or the geometry of space-time is not doing anything too much. And Einstein famously kind of, Harvey gives good evidence that Einstein kind of later in his life wanted to recover something like this instead of that. Because here you have rods and clocks as primitive objects, and that's very weird because rods are made out of little things and they interact in certain ways. So it's kind of strange to go in that route. Okay, so these are two debates. The structural realist versus the dispositional is about symmetries. The geometrical versus the dynamical about, for example, length contraction in the context of space-time. And what I want to show is that there are very interesting parallels between the argument given in favor and against the views in the first debate and the argument given in favor and against the views in the second debate. And not only that, I want to, towards the end, gesture to a way by which, for example, you can combine some of these views to help, like, one of the positions. But I want to be explicit that I'm not necessarily endorsing that position. I just want to show you how you can connect these things in interesting ways. Okay. We can skip that. That's what I said we are going to do. So, unfortunately, there is no time to go into a deep discussion about what are symmetries here. But very roughly, like, it's enough to say that a symmetry is a transformation of something such that certain things of that thing remain invariant. And what is the thing that remains invariant depends on the context. So if you're talking about geometry, you can think of shapes. The transformation is a rotation, for example. The thing that remains invariant is the shape. But in this context, we are not talking about geometry, but we are talking about the symmetries of the laws. Symmetries of the laws are transformations of, I have it here, depends on how you understand the laws, because there is an ambiguity here. Sometimes philosophers and physicists talk about the laws, they're referring to the mathematical equation itself that represents something about the world. And sometimes they just refer to whatever in the world is the law. So you could think of the symmetries of a law from the mathematical sense as transformations of some sort of the variables in the equation such that after you do that, the equation remains invariant. Where that equation here represents a law of nature. Think of Newtonian gravity if you want. Or you can think of the symmetries of a law as transformations of the properties of an object such that after you transform the object by changing those properties, something about the object, for example, its behavior with respect to other objects remains the same. In practice, it doesn't really matter what way we go for the purposes of this debate, but it's good to point out that there is this ambiguity. So if you're thinking of Newtonian gravitation, You can mathematically prove that changes in x and x2 by the same amount preserve that equation. Therefore, it's a symmetry of that equation. Therefore, you say it's a symmetry of Newtonian gravity. But you can also think from the point of view of the physics and translate the planet and the sun by a certain amount, and then you see that the way the planet moves around the sun remains the same. Okay. That's all we need to know about symmetries for the purposes of this. Why are symmetries important? Well, they seem to play a lot of explanatory roles. So going on with Sabrina's stuff, you actually pay attention to practice and textbooks and things. You will see things like, suppose I ask you, why is this stable? Or why this even like exists? Like why my hand doesn't go through? And things like that, why the matter is stable. Most textbooks, as far as I am aware, at some point refer to the symmetries of, for example, the wave function and permutation properties of the wave function and things like that. The fact that there is fermions and bosons and all of that. So at some point they mention symmetries. Also, if you ask why we have the kinds of particles we have, some people try to explain that in terms of symmetries, right? Either they use symmetries to classify these particles in some way, or you can prove that there are certain restrictions on the kinds of particles you could have based on the symmetries of quantum field theory. And also you can use symmetries to explain why, for example, certain properties are conserved, like energy, or angular momentum, or linear momentum, via Emily Nether's first theory. And so, symmetry seem to do a lot of explanatory work in physics. Okay. Now, ontic structural realism is a very popular view that also is very polemic, because how you define it changes a lot from author to author. But for the purposes of this talk, we can take it as saying something like the world has, in some sense, structures, or the world is a structure. And then, these structures are not just mathematical things, otherwise, it's not clear that you are being scientific realist about physics discourse, unless you think the whole world is a mathematical entity, which they don't think. So they think there are these structures, and these are physical structures in some sense. They have certain empirical significance. So there are many variations of structural realism. You can have objects and structures kind of at the same level of fundamentality if you want. You can have structures only and not objects. This was the most radical version, for example, Lediman and others. But obviously they have the problem that is kind of maybe contradictory to say you have structures and nothing being related by the relationships of the structure. So this view, I think, maybe I'm wrong, but I think it's getting a bit out of fashion. And then you have other versions like, well, you have structure, they are more fundamental, and then you have particles as less fundamental entities of some sort. But you can also, and Kerry Mackenzie has a paper arguing that depending on how you define fundamentality, maybe you actually, the only coherent notion you can have is something like you have structures and objects, but the objects are more fundamental. But once you are here, it doesn't look very structural realist anymore, because depending on what you mean by structure, many people agree. You have relationships between objects, and if that's what you mean by structure, everything is fine with that. But anyway, there are different versions, but here is the point for the purposes of our talk. They say, for example, Stephen French is very explicit about this, that all this talk about symmetries and all the theorizing about symmetries is fruitful, because symmetries in some sense capture or correspond to real structures or properties of structures of the physical world. And that's why they are successful, because you are you identify something to be realist about that is kind of explaining why the theories are successful. That's like the thing you should be realist about. Sometimes they talk about the permutation, they talk about the symmetries as the group itself, like the mathematical group that you use to define the symmetries, the reducible representations, and so on. But the point is, these things correspond to a physical thing in the world that is supposed to be doing a lot of explanatory. Okay. On the other hand, we have So this is kind of the standard story about how to make sense of symmetry in the context of structural realism. And actually, symmetries motivated structural realism, at least some of them, like Stephen French's the structural realism. On the other hand, forget about that for a moment. Go back now to another view about laws. Another way of being realist. This is another scientific realist position. Structural realism is supposed to be a scientific realist position instead of an anti-realist. If you go back to, for example, dispositionalism, where they try to understand the success of scientific theories in terms of certain causal powers or dispositions that objects really have, and if you further understand these powers as like their identity as being defined by the causal power they confer to us. So, for example, to have electric charge is to behave in such a way in the presence of an electric field. And you might ask, well, what if there's a possible world where an electron does what a proton does, or something? Well, the structural realist would say, well, that's not possible. That's not an electron. That's a proton. That's how they understand many of the fundamental properties. Now, and for them, also, it's important to mention that laws of nature are either just way of talking about these causal powers, like summaries of the way these properties are related to one another, and these relationships are modal, like they are a necessary connection between some of these properties. Or sometimes they even say there are no laws, but what they really mean is you just have the properties, the causal powers, and that's it, that you don't need anything. Now, the problem in the context of symmetries is that it's just not easy to see how to accommodate symmetries in the framework of dispositional essentialism. Actually, in 1992, Bigelow and others published a paper already pointing to the fact that there are some things in physics, like the principle of least action and conservation laws and symmetries, that don't seem to fit very well with that kind of dispositionalist framework for laws. Why? Well, I mean, think about it. Suppose I say that you have the planet and the sun, and you say Newtonian gravitation is invariant under translations. But you already have the properties of the planet, say to have mass is to respond in such and such way to the presence of, I don't know, gravitational fields, and therefore this thing has to do that. But the invariance itself is like a meta property, as Mark Planck points out. It's not a property of the planet, it's not a property of the sun. It seems to be a property of their behavior that is kind of meta in some sense, right? You are the subject of the predicate there is not like a planet or the star, is like the law itself or the behavior itself. And then things get weird, because are you willing to say then that symmetries correspond to these meta dispositional properties, like dispositional properties the law or the behavior has to, for example, the behavior to remain invariant under translations? That is just starts to sound weird. I'm not saying there is no way out of it, I just say it's not easy to see how in a dispositional framework you actually make sense of conservation laws and objects. And this is why some people, for example, Mark Lang thinks dispositional essentialists could just say, no, like symmetries are just way of capturing things about this first order behavior. That they are not adding anything, I guess, to the world. It's just a useful bookkeeping device. Mark Lang doesn't defend that. He just said this is a view that the dispositionalists could have. Okay. And so maybe symmetries are just bookkeeping devices. And that's why it's hard to fit them in this ontology of properties and like objects and the dispositional properties. Like you're not going to detect the reducible representation of the Poincare rule in that thing, but you're going to detect some particles and like energy spikes or whatever, right? Is what some of them I tried to say. And here is explicitly Anja Chakravarti saying, while there is no doubt that symmetry group comprise a beautiful framework for codifying particles and their properties, all that examining them can achieve in isolation is to generate descriptions of candidate entities. Notice the language of codifying particles and their properties. Like these are kind of like bookkeeping devices, and that's it. Okay. Now, they also, for example, Anjan also points out that there are some problems with structural realism and the way they treat symmetries. One, I call it the explanation challenge, which is like, okay, you, Structur Realist, wanted to explain the success of using symmetries in physics by positing that these structures really exist. But things don't explain by existing. You cannot just, okay, this exists, that therefore you recover the explanations. You need to say more than just positing their existence. So that's what I call the explanation challenge. Second, and it's also related, there's other symmetries in the formalism that physicists think don't correspond to anything, don't give rise to anything. For example, parabosons and parafermions, which are other symmetries of the wave function you can have, they don't lead to anything. And people did try to find some of these things, they didn't find them, and they said, no, these things don't exist. So the question is, in the formalism, you cannot just take the reference to a symmetry and say it exists or something like that. You need to say more because some of those symmetries don't lead to anything, empirically speaking. So that's a challenge. If you only had, if the symmetries in the formalism always led to successful empirical discoveries or things like that, that would be good for your view. But if there are more things there that don't lead to anything, then there seems to be a problem for this kind of inference from the formalism to the world. Okay. The obvious problem for many of you probably already, you probably noticed this, is that if you go through the bookkeeping view of symmetries, you miss a lot of explanatory power, like automatically, right? Like a map can be a very useful bookkeeping device for keeping track of where I am in a city or whatever, right? But I would be very confused if I were trying to explain why a person walked in that direction just by pointing to properties of the map. Similarly, like in this case, pointing to properties of the symmetries do not seem to give you anything, any explanation about what's going on in the real world if you think these are just bookkeeping devices. Okay. Now, so there is that. There is the debate between structural realism and, for example, the dispositional essentialism about how to deal with symmetries. Let's go now to the geometrical debate. Remember, the question was, well, one of the questions is, what explains length contraction? Another question is, why the symmetries of the dynamical laws are the same as the symmetries of spacetime? If you look, for example, at Maxwell's equations, you will see that the covariance properties of the equation are the Lorentz transformations. But this is not spacetime. We're talking about Maxwell equation before Minkowski did anything, so some years before, and you see this thing. You see that the transformation rules for frames in the electromagnetism are covariant, like follow the Lorentz transformation. Why Minkowski spacetime also has the symmetries of the Lorentz transformations? Is this just a coincidence? Like both have the same symmetries, the group associated with the laws and the group associated with spacetime? Well, according to some, like modeling, it's not a coincidence. Roughly what modeling is saying here is that the laws, in this case, for example, the dynamical laws, say, of Maxwell equation, but doesn't have to be Maxwell, it's just one simple example, can only, he says, can only advert to the Minkowski geometry, and it has the same coordinate-based description. So, in other words, this is not a coincidence. The laws inhabit in some way the objects the laws talk about inhabit a space-time structure. That space-time structure has certain symmetries, therefore the laws have to have those symmetries. Some constraint is going on here. Okay. And here is another view. In spatial relativity, the Minkowski metric, which really is referring to the geometrical properties of spacetime in this context when you're talking about the metric, is no more than a codification of the behavior of rods and clones. Look how close this language is to the codification of symmetries in the other debate that has nothing to do about spacetime. Is no more than a codification of the behavior of rods and clones. The appropriate structure for spacetime physics is Minkowski geometry precisely because the laws of physics are Lorentz covariant. It flips the whole thing. The idea here Harvey is saying is something like, no, I mean, you use Minkowski spacetime and that metric because you already have these laws with this transformation, and then you say, well, it would be nice maybe that you imagine that they live in this kind of spacetime. but not the other way around. It's not that the symmetries of the spacetime are constraining the symmetries of the law. So dynamics first, geometry second, if you want a slogan. In the other case, it's geometry first, dynamics second. Okay, and then two challenges that the dynamical account poses to the geometrical account. You will remember the two challenges that dispositional essentialists raise against structural realism. One is the explanation challenge. How can space-time make objects contract? Like, say I say, okay, let's do the geometrical account. There is space-time, it has certain metric, it has a metric of certain kind, and objects inhabit that, and then they contract. But wait a minute. Space-time, what is this metric thing? Is this like a physical thing, or is it just geometrical? And how is this constraining what this rod made out of atoms does? Like, give me a little bit more about how these mathematical, apparently mathematical structures are doing any work here. Can you explain it? That's challenge one, the explanation challenge. Harvey raises this, very similar to the explanation challenge that Anton Chakravarty raises against the structural realists in the other debate. And here is another one that I also obviously call lack of coordination to keep the parallels there, which is you can show that you can have space-times where the symmetries of the metric and the symmetries of the laws do not match. That's physically and mathematically consistent. And that's a big problem, because then where is the constraint? If it's physically and mathematically possible to have this separation between the symmetries of the laws and the symmetries of space-time, then in what cases you have the constraint? It is not clear. You have to say more about that. This is similar to the case of having paraparticles in the other debate. Like, you can have all these other structures that didn't lead to anything, empirically speaking. Here you can have all these kinds of structures too. You can even have spacetimes with two metrics, biometric spacetimes. And then the matter only follows one of the two. But that's weird, how this rod knows which metric to follow. Exactly. Well, I guess that's a good question for the geometrical account. Okay, to end, I want to show you how you can kind of use some tools from ontic structural realism to partially meet some challenges that the geometrical account faces. I introduced you to geometry and structure, and the idea is like some sort of combination of the geometrical account and ontic-structural realism. And I don't think it's that, I don't think it's necessarily more weird than anything structural that the ontic-structural realists were already doing in the context of particle physics and quantum theory. And so imagine, for example, suppose you are an ontic-structural realist and you have to explain the contraction of rods under Lorentz transformations. Well, maybe you think that the metric is a structure. Just as you thought that all these other symmetries in the other contexts correspond to a structure, a real, by structure, I don't mean just a mathematical structure, I mean some sort of physical structure in the world, and you say that it has some empirical significance. Just as you say, as a structuralist in this debate, that other structures have empirical significance, otherwise it's just you're positing mathematical things, or things there that do nothing, and so they don't have explanation power of any sort. And then suppose you are a moderate structural realist, so you think that objects are rod with atoms exist together with the structures, for example, the metric structure. And finally, you have to say something like there is a structure that corresponds to the dynamical law itself. Why? Because remember, you have the spacetime with, for example, a metric. If we are being structuralist about this, you can posit the metric corresponds to a real structure. And then you have the dynamical law also has symmetries. They happen to coincide in the case of special relativity that we are familiar with, but they don't have to. And so you say, well, the law itself in a way encodes or has or corresponds or is associated with a structure. What structure? The symmetries. The ones captured by the symmetries of the law. How this helps in any way? Well, think about, remember, you have to say that the structure has to have some empirical significance. If you are not to structural realism in the context of scientific realism, what can that be? Well, I just don't know what could it be except that the metric structure constrains the structure associated with the laws. Like, these structures, just as in the case of, for example, quantum mechanics, the structures of the permutation group are supposed to constrain what kinds of particles you can have, like Fermis or, for example, or bosons. Here, the metric structure somehow constrains what kinds of dynamics you can have. By constraining the dynamics, by constraining the symmetries of the laws, you indirectly constrain what objects do, because what the objects are governed or satisfy these laws are being constrained in some way of constrained by the metric structure. So basically, we are being realist about the metric structure, and that's doing a lot of work here. And so you can imagine you have space-time, you have the symmetries of space-time, these little cones, it's a Minkowski symmetries, right? So the Minkowski or the Lorentz group. And then you have the symmetries of the laws, and they are like this because it's constrained that. And then this is supposed to explain the behavior. This is just a sketch. I'm just giving you like the bare bones of what a structure realist could try to do in this case. The problem, however, is that the lack of coordination challenge, I'm not completely satisfied with this kind of approach, because if it is true that mathematically and physically you could define cases where the symmetries of space-time do not coincide with the symmetries of the laws, right, and here. For example, here you have Minkowski symmetries, but here you have a weird thing, and then the rod does a weird thing. Here you have no-Lorentz symmetries, but the laws happen to be happen to satisfy Lorentz transformations, and then the rods do contract. If this is possible, like you as a structuralist will have to grant that the metric structure, you shouldn't be realist about the metric structure in cases like this, because there is a complete, the things you measure in an experiment are at the end of the day particles or fields or whatever, and the contraction, right? But you don't access the metric structure directly, if not through the rods and the clocks. And if you don't access that directly, then like it seems you have to just stop at the level of the dynamical laws in these cases. And so the metric structure loses empirical significance because there is a disconnection between it and empirical work. Okay, so to conclude, that was a very quick sketch. I just wanted to show you how, if you were to be a structural realist in the context of the other debate, there is a natural extension of that to the context of this debate. You might think, well, it doesn't work. It's weird how this constraint actually works. Well, you can raise that question to them in the other debate too, like how the constraint is supposed to work in the case of the permutation group. Well, whatever you say there, you try to say here. So I show, for example, that the geometrical account and the ontic structural realism face very similar challenges, like the explanation challenge in both, right? You can say that you posit the existence of symmetries, but that doesn't seem to be enough to recover an explanation, a genuine explanation. First, case of the structural realist here, in the case of spacetime. You can say, oh, yeah, sure, the geometry of spacetime makes rods contract, but saying that doesn't seem to explain much. That doesn't seem enough. It seems you need to say more. And then the other challenge that both seem to face is that there are more structures in the formalism than what physically we seem comfortable with, right? Like in the case of symmetry, there is all these other symmetries that do not correspond and do not lead to anything that you could find in an experiment. In the case of spacetime, you can show that there are all these weird models where you can have symmetries of the metric, like weird metrics where they do not match the symmetry of the Minkowski laws. And finally, this is one side. The other side is, suppose you say, okay, you know what? These structures are weird. I just think they're bookkeeping devices. In the case of structural realism, the symmetries, for example, are just bookkeeping devices. But if you say that, then you lose the explanatory power that seems to come from positing things like symmetry, for example, the stability of matter, and other examples I mentioned before. And in the case of spacetime, this is more questionable, but some people do think that there is a lot of explanations that appeal to the metric. And if you're not a realist or you do not commit to the metric, and you have just the laws, maybe you are losing certain or explanatory power as well. And that's all. Thanks.
All right. So bad news is that Alexandre Eira, who was supposed to give the comments current with us today, he asked us to read the comments. I'm going to do that now. All All right. Making a connection between seemingly distinct philosophical debates always makes for an interesting project that usually bears fruit. In the worst case scenario, one can always find that there is no connection, which is by itself interesting. That being said, the link suggested between dynamical and geometric conceptions of spacetime and dispositional and antique structural forms of scientific realism seems to be particularly apt for a variety of reasons. For one, given the degree of mathematization of our modern theories of spacetime and matter, pondering whether the metric is a structure in the relevant sense is only natural. As Sebastian notes, it's a move very much in the spirit of OSR. Second reasons, not only that, but importantly, it's also the case that the similarities noted between the styles of argument levied against structural realism and those leveled against geometric accounts seems rather robust. Third reason, finally, research into the nature of spacetime and the role of the spacetime metric is perhaps particularly in need of reconceptualization, given the somewhat awkward situation in which general relativity leaves a classic substantial versus relational spacetime debate. New manners of spelling out what is at stake metaphysically are rather welcome. The paper presents two main points of contact between the pairs of views through the lens of the criticism against antique structural realism and the geometric conception. Both seem to struggle with the nature of the interaction between spacetime structure and material entities, and with the fact that metric structure can fail to constrain the symmetries of dynamical laws. My comments will focus mostly on the former issue. It's suggested that an OSR approach to a geometric account, the so-called OSR view, could go some of the way towards answering the criticism against it. One aspect of the argumentation that will likely benefit from further clarification is the notion of structure in use. While the paper does not intend to advance its own doctrine of structural realism, nor does it need to pick a particular version of the position, it seems to me that something more needs to be said about the nature of physical structure, and in particular about how physical structures are interrelated to provide a solid case against the dynamical account. Note that OSRG makes claims about the existence of two distinct kinds of structure: the metric structure that represents or otherwise corresponds to physical geometry, that's assumption 1, and the structures corresponding to the dynamical laws that govern the motion of matter, assumption 4. The first difficulty for the geometrical account, namely how come particles know about space-time they are immersed in if they don't have space-time fillers? I'm using these two notions, you know what I mean? Or how come space-time makes bodies contract if it's not material in the usual sense of the word? Stop. Isn't solved by claiming that the physical metric structure constrains the structure of dynamical laws. However, at least without a further account of the relationship between structures, it's not clear how the metric structure constrains the structure of dynamical laws. Even more crucially in the discussion with a supporter of the dynamical account, it's not clear why the metric structure needs to constrain the structure of dynamical laws. To put the point a bit more clearly, note that the dynamicist's contention is that, on balance, there is no good reason to think that the fact that dynamical laws coincide in their symmetry structure is any more than happenstance. The dynamicist might then reason, according to OSRG, there are cases where realism about metric structure is not justified. Namely, there is no metric structure, and nonetheless there is presumably still structure associated with dynamical laws. So it's not metaphysically necessary in the view that there be metric structure for there to be structures associated with dynamical laws. But then, even granting that there is such a thing as a structure of dynamical laws, why should it be necessary that there is additionally metric structure in the cases where the structures of various laws happen to be similar in certain regards, namely happen to be partially isomorphic. To be clear, the difficulty seems by no means untreatable. There are certainly answers available to the proponent of OS or G, perhaps having to do with how metric structure constrains model facts about dynamical laws, or alternatively on account of how metric structure and the structure of dynamical laws both represent aspects of the structure of the world and so don't really come apart in the way supposed above. That notwithstanding, given that precisifying the nature of structures seems to be a perennial issue in the author literature, it's likely worth paying additional attention to the matter so that, in the attempt to shine a light on the dynamic geometric debate, one is not directly importing OSR's difficulty. Without going too deeply into further issues for a matter of space, the direct link between OSR and the geometric account also suggests interesting connections to other debates besides the above central thought. The discussion could surely be expanded in many directions. To highlight one such direction, in this case a connection with the classic question of the nature of spacetime, it's interesting to note that although OSRG is a geometric account, it's arguably not an account of substantival spacetime. Though spacetime constrains dynamic behavior, it's not a necessary self-subsistent entity in every possible world, both within Newtonian and relativistic physics. At the same time, it's difficult to see why one should even consider classifying it as an account of relational spacetime. Perhaps the breakdown of the old categories shows how the project shines a genuinely new light on the topic. All right, I'm done. If you want to take some comments.
So, yeah, I think it's a very fair point to add more pressure on what the notion of structure is being used here. So I think Alexandre is right about that. I think that's a problem for structuralism more generally. As I was saying, depending on who you ask, they will try to spell out the details about structure a little bit differently, right? The most pressing question, I guess, at least as far as I interpret those comments, is, well, how are these structures constraining anything? In the case of geometrical account that I presented, why do you even need to posit the structure of the metric as something that exists and not just stay at the level of the dynamical laws and the structures there? So, I guess the first thing I want to say is that I don't think I am structuralist, at least not in the traditional sense. And for me, it's also hard to understand what this constraint from the structure towards matter or dynamical behavior exactly means. If you look at what Stephen French says in some parts of his book, he says that these structures have modality, that they are modal in some way, because he's not a human, and so he wants to recover to a certain extent this necessity that you seem to associate with laws, at least if you're not human. And so he thinks that structure in some way have some modality in them. He has a whole chapter about that, but actually, besides saying that, I don't know what else I can say. Like, their structures have some modality inherited to them. And also, like, he doesn't think that you have the objects are being complete, because he's very skeptical of objects, at least in the particle sense that you were talking about before. And so, it's not that this thing constrained an electron understood as a particle, it's that the electron itself, I guess, is a structure of some sort, for example, associated with some representations, associated with the symmetry groups of the wave function, or something like that. And then it's somehow constrained. If you see Michael Esfeld has a paper where the structures constrain the world by being causal. They cause things. The structures have causal powers in some way. For example, this is not in French, but this is Michael Espen. But if you say that structures have causal powers, you start to blur a little bit the distinction between structural realism. If you, for example, suppose you think structures have causal powers and objects exist, like particles in addition to structures exist. Well, I mean, if by structure you mean some sort of relationship or some sort of n-tuple property that particles or objects can have, that seems to be fine for dispositionalists too. They think properties exist and they think they are related in some ways. These relationships can be captured in structural talk if you want. So the boundaries start to get a bit blurry depending on what version of structures and what version of how they constrain the physical world you adopt. Having said all of that, if you want to, so actually to give more context, back in the day, and by that I just mean maybe 2008 or something like that, actually one of the main challenges for ontic structural realism raised against Ledima, for example, and Ross, is what later became called the Chakrabarty challenge, which was like how these things interact with the physical world, the things happening in the lab, because they want to be scientific realists. Scientific realists get their evidence from experiments to a good extent, but how do you connect those experiments to structure talk? And that, called Chakrabarty challenge, which you can just call the causal challenge about how these empirical things relate to the structure, remains, I think, unanswered. Or at least, I mean, there are some attempts, even in French, you just have to say this is a primitive thing. These things constrain behaviors, and that's it. The explanation has to stop somewhere, it stops there. Besides that, I don't know, I mean, I don't know what else I could say in defense of the structure, at least. I do think that the other comment about the metric case is fair, and that's actually why I think I put a star in responding to the lack of coordination challenge. Because it's true, if you are a structural realist and you are trying to understand the space-time debate between the dynamical and the geometrical, and if it's true, as it seems it is, that you can have symmetries of space-time that do not match symmetries of the laws, then why don't you just stop here? You say, yeah, there are structures here, if you're a structural realist. The structures have to do with the symmetries of the laws, the dynamical laws, right? And this is what is going to explain, or this is what's connected directly to the behavior of rods and clocks, or particles and things like that. And just stop here, like, or be skeptical about this, or I don't know, agnostic about what is going on at the level of the structures of space-time. Maybe they exist, maybe they don't. Maybe they exist, but the point is they don't seem to be connected to the empirical realm. And so, depending on what kind of scientific realist you are, you might be kind of worried to go that far, to commit to these unobservable structures that don't seem to constrain in any interesting way the things happening at the upper level. So yes, maybe an ontic structural realist would like to stop here, but if they stop there, they become dynamical ontic structural realists. They are not helping the geometrical account, or at least it's not clear how, because the geometrical account wants to say that is the structure of space-time that explains why things here do what they do. If you stop here, you cut that, and you become the dynamical account combined with structural realism.
So this is a fun part. I'm a little puzzled by some of your the objections kind of on either side. One is the bit about explaining behavior by appealing to a map. Certainly that's a thing that we can do. It's just that bookkeeping devices, when they explain, their explanations are sort of preferred, or they explain by way of appealing to something else in the world that explains, right? So when you explain, you know, if you were to like notice that I'm all wet, and then you would see me walking away, and so where is he going? You look down, and you point at a map, you're pointing at the part that says umbrella store, you know, pretty close to here in roughly that direction. You're like, oh, it's because he doesn't have an umbrella, right? But like the thing that the bookkeeping device is doing is explaining by way of appealing to some other further thing. That's presumably what the dynamical sort of explanations are expecting the bookkeeping device to do. It's not that they're explanatory sort of entities on their own, but that there are tools for picking out explanatory things. And sort of related to that, this worry about the how space-time can make objects contract. I was kind of puzzled by this from like physical reasons, because certainly in 99+% of cases, the answer is it doesn't, right? So both time dilation and the shrinking of objects, that's a symmetric effect, right? It's a like this is like what like one this is a coordinate dependent and symmetric effect. Like it will look to the other moving thing, like the thing that's sitting back on the shore is also shrunk in the same way and also moving slower. It can't be both, right? So certainly if it's not that it's shrinking both of them somehow in a way that it makes both smaller than the other. It can't be doing that. It is true that sometimes there is, sometimes something like that is happening, right? In the case of like with Bell and the two rockets, and like the string between them. But in those cases, the thing that's happening is roughly that when the whole system is accelerated over the process of that acceleration in the space-time of that structure, you end up in a situation where the thing is sort of stretched. And because of the kind of physical thing it is, when stretched out, it is out of equilibrium and then pulls itself in order to get back into equilibrium. So like the shrinking is actually done by all of the sort of physical things that make up the object, and the fact that it's, which is why like if you thought it was made of silly putty, they would just stretch out a little bit. It would change the...
So thanks. The first thing about the explanation, sure, what the dynamical person is going to say, or the disposition, depending on what debate you're talking about, they're going to take this bookkeeping talk as indirect talk to refer to things about the properties. The problem, however, is that they seem to get explanatory redundant. Like they haven't spelled out, like you cannot just say, oh, this is just way of talking about these first order properties of the objects and stop there. Because, well, to spell out the details, you have to say, well, what exactly you are saying about these first order properties and how you recover the explanation that like physicists seem to recover from that. So for example, Bigelow in that paper says, there is no room, explanatory room for these things. You have the dispositions and the objects, and you explain the behavior of, say, electrons or whatever. And that's it. And if you say, well, and then you have these properties of the properties, for example, that would be a route to go back from the symmetries to the things you think exist, like dispositional properties. The question is, what does, I guess, higher order properties of the disposition of the causal powers? Do you understand them themselves as dispositional? Do you understand them in other ways? And if they are understood dispositional, what are the dispositions and what are the behaviors that they are supposed to relate? So one option is, for example, you could say, to be invariant under translations, you can make that dispositional by saying, is to have causal powers such that those causal powers are themselves instantiated by a particle, and that particle were to be translated in space or something like that, then the manifestation of these causal powers will lead to the same outcomes in certain experiments, something like that. But it's not clear how this referral back to disposition through the symmetry talk works. It seems it's maybe easier to just say, no, there are dispositions, there are these properties, and these higher order properties, I'm not committed to that. But yeah, I mean, it's a fair point. It is, I guess that's one thing that the structuralists raise against them, not me in particular. Like they say, well, go ahead, do this in dispositional talk. Right, do it, please.
I'm afraid to interrupt, but if you want to have the other questions.
Yeah, no, okay, sorry, I extended the talk. And the second point is a point I think is also very good, and I think it's something I have struggled understanding sometimes in the debate in the geometric versus the dynamical account. I think here it matters to distinguish between active and passive transformations. I know Maudlin wants to treat them equivalently. Like he wants to say, well, you can you can understand this from the perspective of this thing moving with respect to this, or this thing moving with respect to that. But And here is where things get tricky, because if it's how things look, like if you say, oh, length contraction is just how this rod looks from the perspective of this other frame, that's not quite true, because how things look is very different from the Lorentz transformations. Then you have to take into account how light behaves, and you have weird effects in relativity. So you're not really recovering like a thing about how things look. You're recovering something like, I guess you don't want to say it's about how things look, because how things look and how things contract come apart in special relativity. So that's one thing I wanted to say. But the other more substantive thing is that it's symmetric, so you can move here or move there, right? And I think what the dynamical account is going to say is that so pick the system you want to analyze, and like you say the electron here, this is what I want to understand, then boost it with respect to you. The Maxwell equations entail that the thing is going to contract, and you don't have to contract in the sense that the distance between the parts of the atom are closer now. You don't have to refer to space-time. You just look at the Maxwell equations, look at the transformation rules, and you see that the distances between, say, this part of the atom and this is smaller with respect to the outside perspective. And then you can do it from respect to the other one. So yes, they would say, I think they would buy the valid and say it contracts in this sense of contraction from the Maxwell equations. We can talk more about that, but they would buy the bullet in that case. John Bell, for example, has to do something like that in this how to explain special relativity.
I don't think he definitely doesn't go for a...
I'm sorry, but there won't be time for anyone else otherwise.
So earlier in the talk, you explained the attitude that thinking of symmetries as dispositions seems weird. So at first I thought that was wrong. Now, in light of what you just said, I think it's right. But I can say a little bit in 30 seconds or a minute about the nature of the weirdness. Which, so why aren't symmetries dispositions? The disposition of water to boil is if you heat it to such a degree, then such and such will happen. Similarly, symmetry, if you rotate the circle, then it will work the same. So both have the same if-then structure. The difference is that to be a disposition, there has to be a law-like connection between the antecedent and the consequent. In the case of symmetries, the nature of the law-like connection, and it may not be just one kind of connection, it may be more than one kind of, different kinds. In different situations, you may appeal to different sorts of things, but it's a difference in the nature of the law-like connection involved in the disposition that makes us feel different from physical dispositions like the disposition of water to oil.
Good, thank you. Yeah, I'm more sympathetic to trying to make sense of symmetries in the dispositional talk. I don't think it's a knockdown argument from the structuralists. I do think, like, if you try to do it in terms of, as I was saying, to see manifestation conditions, like, oh, to do this in the context of this condition, you need a law, as you said, to connect how these things are related. The thing is, now you're talking about symmetries are properties in the traditional sense of laws, right? Not of a particle, say, exactly, but about the behavior, because I'm talking about dynamical symmetries, not the other kinds. There are many kinds, as you know. So when you think about that, then you have a behavior, say, a law-like behavior, and then you want to say that behavior itself is symmetrical under certain transformations, like translations or something like that. It's just unclear now what the thing is to which you are attributing the dispositional property. That's one of the, I think, weird things, because it's not the planet, say, or the sun, it's their behavior, right? But maybe that's fine too. Maybe that's, you can say, yeah, behaviors also have dispositional properties. I think Amgen at some point might want to go along those lines. But then what is the connection between the manifestation? I guess in this case the manifestation and the It manifests, well, yeah, it's not so clear what the law-like connection, as you said, between the things related by these meta-dispositional properties are. Yeah, good, and like if I want to add something more, like the principle of least action is another hard case for the dispositionalists, because they try to say, well, maybe there is this Lagrangian property of being disposed to minimize the path of action, no matter what, basically. No matter what, you're going to minimize the action in the trajectory in spacetime. That's a weird dispositional property, or it sounds weird. So if that sounds weird, maybe the other ones also have to sound weird for similar reasons. That's kind of the concern, but yeah, I think pretty much agree with you. Yeah.
Okay, good. Thank you.
Yeah.
Right, I'm sorry, but we are out of time, so join me and thanks, Sebastian.